test which they conducted at 10:30 on Wednesday every week. So please do not be alarmed. It's fine. Okay, so we hand this to the session chair.
Thank you. Okay, so good morning and welcome back to the session on the advanced encryption. And so the first talk in this session is about traceable receive-free encryption by Henri de Villiers, Olivier Pereira, and Thomas Peters. And Henri, you give the talk, please.
Thank you. So yeah, I'm Henri de Villiers from UC Louvain, and I'm going to talk about traceable receive-free encryption. It's a joint work with my supervisors, Olivier Pereira and Thomas Peters. So the main motivation and application is electronic voting, and especially electronic voting protocols that have a non-interactive ballot submission. That is, we want electronic voting protocols in which, for the ballot casting, the voters come and only send one message to the voting server. And so it's simple and easy. They just send one message and the casting is done. So when we design such systems, we usually have a public voting board on which people can post publicly on this. And this message they post are usually the encryption of their vote. And to build the system, we want some security properties. And for electronic voting, the two main properties are verifiability and ballot privacy. In short, verifiability means that a voter has some guarantee that their vote is correctly recorded on the bulletin board, and that the result of the election of all the ciphertexts put on the bulletin board is correctly computed. While ballot privacy means that there is no leak about the information, the vote of a voter, except of what you can learn from the result of the election. And so to achieve these two securities, we usually use some cryptographic tools. For verifiability, for example, we put on the bulletin board some zero-knowledge proofs that everything is computed correctly. And for the ballot privacy, it is shown that if you have an MCPA secure encryption scheme, then it's possible to get ballot private elections. But is that all? Actually, there are other privacy issues. If you use such a system, the voters can prove to another party how they voted. So if the voter is adversarial also, it can give to some adversary an opening of the encryption. For example, you can give the vote and the randomness of the encryption you put on the bulletin board, and the adversary can then check on the bulletin board and verify how the voter voted. So ballot privacy is not enough, and we want also to build some protection against such attacks. There are some ways, some mechanisms to protect this. The two possible ways is either to ensure that the voter cannot produce any opening of the vote in polynomial time, while the other way, on the contrary, is to make it easy for the voter to provide an opening for any possible vote. In this work, we focus on the no-opening solution because we want to build a non-interactive ballot casting, and we do not want to rely on any PKI infrastructure built for the election. We want to keep things general and do not make such assumptions. So we will focus on the no-opening solution, which does not require such things. And now there's several ways, again, to do this no-opening solution. And we focus on re-randomization of the ciphertext solution. So we assume there's another party, the randomizer, and the voter can give a ciphertext to this another additional party, which will re-randomize the ciphertext and put it on the bulletin board. And so now the randomness is refreshed. And since the voter does not have any clue about what is the randomness of the randomizer, he does not have an opening of the encryption anymore. But doing so, we still need a verifiable election. So if the randomizer put a new ciphertext with a new plaintext, a new vote on it, the voter will not have a guarantee that his vote is correctly counted. And so to have this verifiability, again, there are some ways. You can make a zero-knowledge, a Sigma protocol to prove to the voter that the randomization is correctly done, but this requires interaction. Or you can use a designated verifier proof also, but again, it requires interaction or API infrastructure in the beginning. And so we will want to find other solution that does not require these things. So there are existing solution back in the days. So I think the first one using this paradigm of randomizing server is from Earth et al. And it's based on designated verifier proofs. And more recently, Blazid et al., and especially the Belenius RF voting systems, use signatures on randomized ciphertext, which are a nice primitives that allows the voter to encrypt the ciphertext, and using a signature key they receive from the registration, they can sign their ciphertext and send it to the randomizing server. And the signature has some updating property. So when you randomize the ciphertext, you can also update the signature to randomize it. And it's still a valid signature. But on the other hand, if the randomizing server wants to encrypt a new vote, it's not possible because it does not have the signature key. And so this solution is RCCA secure, but actually we show that we find out that it's not enough to guarantee receipt-freeness. So we need something stronger than RCCA security. And also about efficiency, the construction uses bit-by-bit encryption. Yes, we are looking for something more efficient. And so in our solution, we identified the exact security notion that we need for receipt-freeness. A bit like NMCP security is enough for ballot privacy. We try to point out which exact security notion is required for receipt-freeness. And then we build, we construct for this new primitive, new constructions that support encryption of group elements that are more efficient than the bit-by-bit encryption. So to do so, we introduce a new algorithm, trace, because we want to allow the voter formally to check on the bulletin board where is the ciphertext. And this trace algorithm is inputted a ciphertext and outputs a tag. And this trace is invariant to randomization. So when the randomizing server sends a randomization of the ciphertext, the trace is preserved. And so the voter can check on the bulletin board if there is some ciphertext with the initial trace. And if this is the case, this is the ciphertext of the voter. There's also a critical point here. We need this trace algorithm to, so we need the voter to be able to encrypt any possible vote to give some trace. If the trace depends on the message, then we have some issues because the trace would also be a receipt for the receipt-freeness attack. So the trace should not depend on the message. And so for this trace algorithms, we want to protect against the verifiability attack. And so we introduce this kind of unforgeability game in which the adversary can send some message to the challenger and receive the ciphertext. And then the adversary wins if he managed to find a new ciphertext that has the same trace, but decrypts into a new vote. And if this game is hard for the adversary, then it's quite straightforward to show that the voter has good guarantees that when he sees his ballot on the bulletin board with the trace, then the vote is indeed the vote that it sends the adversary. And you can see that we also send the secret key to the adversary. And this is also critical because even though in the real world, the randomizing server does not have the secret key of the election, it cannot decrypt the vote, we still want to have some protection if the adversary and all the election officials are corrupted. We still want the verifiability to hold if everyone is corrupted. And so we also put the secret key, we also give the secret key to the adversary to cover such cases. And now that verifiability is taken care of, we also want the receipt-freeness. And a bit like NMCP and NMCP security, we introduce a new security game that is reminiscent of this CCA game. But usually in these CCA games, the adversary can send messages to the challenger and receive an encryption of these messages. But in the receive-print game, actually what happens is the voter sends to the randomizing server a ciphertext and can see on the built-in board a randomization of the ciphertext. So this is a different blueprint, and we cannot reduce to this game, to this sending of plain text games. And so instead, and the main core of this definition is that we send two ciphertexts to the challenger, and we receive one randomization of this ciphertext. But the game is at the moment easy because we have the tracing algorithm, and so if the traces are different, we can easily distinguish the ciphertext. And so we put a restriction on the challenge, and we make sure that the traces are equal. Otherwise, it's too easy. And also, since the ciphertexts are malleable, if you randomize it, it would be easy to win the game. And so we ensure that the trace of the post-challenge description are different from the challenge ciphertext. So this is the TCCA security. And using this game, it's actually quite easy to show the receive-print definition security if this game is difficult. And now I can define this new primitive that is traceable receive-free encryption, or TRENC. It's a normal, usual encryption scheme with gen, enc, and dec. So we had rend and trace, which are the two algorithms I talked to you about. Also lgen and lenc, which are a bit technical, but this is to make sure that the voter have some way to encrypt any message to get a possible trace. So LK alone determines the trace. So the trace is independent of the message, and using LK, the link key, you can just encrypt any message for one given trace. So if we have this primitive with TCCA security, traceable security, and also randomizability, which ensures that the randomization of a ciphertext is indistinguishable from a fresh ciphertext, then this is what we define as a traceable receive-free encryption scheme. So now that we've defined that, we also want to construct it. And so we give several constructions. First, we provide the generic constructions using known tools of what we already know. It uses also signatures on randomizable ciphertext. It uses a randomizable proof system, gross-side proofs, LHSP, linearly homomorphic structure-preserving signatures. But all the generic constructions that we manage to achieve, they give stronger security. We do not manage to get exactly the TCCA security because we also need at some point in our constructions to extract the link key. And so we need some additional properties using the known tools. And so we go forwards, and we also build a direct construction that do not need this additional property. And this direct construction is string-based and based on SXDH and use SCRs. So I'll try to give some intuition about this direct construction. The first element of this is a CP encryption, C0, C1, and C2. And now it's very malleable. So we want to add some simulations on proof that this C1 and C2 are in the span of GH. And we use techniques that are reminiscent of tag-based encryption. And so we will use the tag as the trace, which is the unmalleable part of our ciphertext. But there are some technical challenges. We cannot use selective tag encryption exactly because the tag is not chosen before everything. The tag can be chosen at any time, and especially during the challenge. And yeah, it makes the game more difficult, the reduction more difficult. And also the pre-challenge decryption, yes, requests can use also the tag, the challenge tag. And so, yes, we managed to solve that using, again, linearly homomorph structure preserving signatures to build a proof that this vector, C1 to the power 2, C2 to the power 2, C1, C2, is in this span, which is one step toward TCCA security, but we also want traceability. And so to do so, we have another LHCP signatures of this matrix, where the key are here, and basically the secret key is the link key of the signature scheme, and the hash of the verification key can be seen as the trace and as the tag of the tag-based encryption. To give some intuition, the first row, the signature of the first row is a signature on a message. But when you want to randomize the message, the first signature is not valid anymore. So you want to also update the signature. And so this is what the second row is for. If you use the homomorphic properties of the signature, you can obtain an updated signature for any randomization of the CP encryption. And the last row is for technical reasons. This capital F and capital G are in the span of FG initially, but in the reduction, we embed a DDA challenge to make it easy to randomize the CP encryption at some point to hide the message. We also use cross-site proofs to write some elements in all of this. And yes, finally, we have to make sure that everything there is randomizable except for the unmalleable part, for the tracing part. And in the end, as you can see, we do not use bit-by-bit encryption. We managed to only encrypt a group element M, and we have ciphertexts that are relatively small in size. And once we've built this trunk, it's not very easy to obtain a receipt-free voting system. We have a generic transformation that take a trunk and outputs a receipt-free voting system. And the nice thing is that all the usual properties for voting system are preserved. The verifiability still holds, even if everyone is corrupted. And regarding privacy, even if the randomizing server is corrupted, it still cannot get any information about the vote of the user. Actually, if the randomizing server is corrupted, the only thing that we lose is receipt-freeness, which we do not have if the randomizing server does not exist. And so in conclusion, we have three main contributions. The first one is this new security, this new primitive trunk that capture the exact security properties that we need to build receipt-free systems. Then we have two constructions, a generic one and a direct one under SXDH. And finally, a generic transformation that from a trunk scheme outputs a receipt-free voting system. Thank you for your attention, and I'm happy to answer any question.
Thank you, Henri, for the presentation. So you have time for question. Any question? So you mentioned in the existing work that we can use signature on the randomized ciphertext.
Yes.
And there's some disadvantage that we need to do interaction with the authority to get the key or something like that. And
not so we use it in our generic construction, but we do not have to trust the authority. So that's one nice thing about this new voting system, is that contrary to Berlin yourself, we do not trust anyone. So the user can generate the signing verification key of the SRC primitive and use it for the trunk. So we do not trust anyone for the verifiability or anything.
Okay. Okay.
Yes. Yes, we have to trust the CRS. Yes.
I guess there's some question online.
Yes.
Here you cannot. I cannot see the question online. Okay. Yeah. So there's one question from Evasion. If not give original coins, is not this a proof how he voted? As the two tag would match.
I do not understand the question.
So sorry, I'm not sure you can hear me, but I probably
Yes.
misunderstood your primitive. But even though you re-randomize the ciphertext, you don't have coins for the final ciphertext. If I want to sell my vote, can't I give my original coins, and then because the tags are going to match, everybody knows, you know, how I voted?
Yes, so you can give that, but there is no proof that you do not lie. You could give any ciphertext with any coins, and for the attacker, the receipt-free attacker, he cannot check that this ciphertext is indeed what you send to the randomizing server.
Got it. Even though it has my signature on the tag or something like that.
Yeah. Yes. So with the link key, for example, you can create a ciphertext for any message that has the same tag. And so you could cheat and say, okay, this is a new ciphertext for this vote, while you send another ciphertext to the randomizing server.
Oh, so the tag is not collision resistant. You can easily find collisions for the tag.
Yes, yes, and it's critical. You need this property, otherwise receipt-freeness is broken.
Okay, thank you.
Yes. So yeah.
Another question? So if not, let's thank the speaker again.
Thank you.
The second talk will be online.
Hi, this is Shikhar. Can you hear me?
Okay, we can hear you. Oh, great. Okay, so the second talk in this session is about efficient searchable symmetric encryption for join query by Charajit Jutla, Sika Paranabis, and Sika will give the talk. So please.
Yeah. Thank you very much for the introduction, and hello and welcome everyone to this online presentation on efficient searchable symmetric encryption for joint queries. This is joint work with Charanjit. So the setting for this talk is that with the advent of cloud computing, organizations and clients can outsource the storage and processing of extremely large databases to third-party cloud service providers. And at a later point of time, any organization could issue a query request to this data and obtain the corresponding result. This would, of course, be very simple and efficient if the client trusted the third service provider to respect the privacy of their data. But this is not always the case in today's world. And the client might not trust the cloud service provider to respect the privacy of their potentially sensitive databases. This leads us to the realm of what we call as computing on encrypted data, where the client can use a cryptographically secure scheme to encrypt the database before outsourcing it to the cloud service provider. But this then makes it challenging to issue query requests and obtain the corresponding results. In particular, the client might not only want to protect the privacy of their data, but they might also want to hide the kinds of queries that they're issuing on the data, because these queries might themselves be sensitive. So the aim is to basically enable directly computing queries on top of the encrypted database without revealing to the server either the data or the queries to the maximum extent possible. Now, an ideal solution for computing on encrypted data would be one that would provide efficiency close to plain text searches, for example, while also leaking very little information to the server. Unfortunately, the existing solutions today lie at two opposite ends of the spectrum and don't quite achieve this ideal guarantee. For example, on the bottom left, you have solutions that are cryptographically elegant and provide strong security guarantees, but are unfortunately quite inefficient, at least today, and do not necessarily scale to extremely large databases in practice. And on the upper right-hand side, you have schemes that are sort of motivated by database techniques, and they are quite efficient and allow processing a rich set of queries on encrypted databases. And they're also quite scalable, but sometimes they tend to leak quite a bit of information about the database and have been subjected to certain leakage abuse attacks, which can be used to break the query and in certain cases, data privacy of these schemes. In this talk, I'll be talking about a class of encryption schemes called searchable symmetric encryption, or SSE in short, that lies somewhere in the middle of the spectrum. in the sense that SSE provides some kind of trade-off between security and efficiency. It leaks some information to the attacker and is hence not as secure as the schemes on the bottom left. But at the same time, this leakage is not so much that it can be used to break the data or query privacy of the schemes, right? So that's the aim of SSE. And SSE, is not alone in this spectrum. There's also solutions based on trusted hardware or trusted execution environments, for example, Intel SGX, which also allow, querying the data by bringing it into a secure enclave. But in the case of these kinds of solutions, we actually trust the hardware to serve as a black box, which the adversary cannot peep into. And this is sometimes not the case because of the presence of side channels and other mechanisms by which the adversary can get some access to the data. On the other hand, in SSE, even though we can probably support a slightly less rich set of queries, we rely purely on cryptographic security guarantees and do not trust the hardware. So here's a very brief one-slide summary of SSE. I'm not going to go into any formal definitions, for which I would refer you to the paper and also to the rich body of work on SSE. So at a very high level, we have a client, which is the owner of the data. And for simplicity in this presentation, I'll assume a single reader, single writer setting, where the client is the only entity which can actually issue queries on this data. Of course, SSE can be generalized to other settings, such as the single writer multi-reader setting, where there's a single data owner, but many other clients are allowed to issue queries. But I'll not go into that setting for this talk for simplicity. So the client typically holds a cryptographic key, which it uses to encrypt the database and put it on the server. And at a later point of time, it uses the same key to issue queries, which could either be search queries on the database or update queries to update the data. And we typically assume for SSE, again for simplicity, that the server is honest but curious, or semi-honest, in the sense that it does not deviate from the protocol, but tries to learn some information about the client's data and queries. So with this setting, I'll now go ahead and present our main contribution. In this paper, we present join crosstags, or JXT in short, which is a practically efficient SSE scheme for computing queries over equijoins of pairs of encrypted tables in encrypted relational databases. So this is our main contribution, and here is an outline for the rest of the talk. So I'll first provide a background on what we mean by equijoins of tables in relational databases. I will then provide a brief overview of our main contribution, which is JXT. I will then provide a brief overview of our techniques. And finally, I'll end with some open questions. So here's an example of equijoin queries over tables. Let's suppose that this is a toy example. So I'll just present two very simple tables here. Let's say we have a transactions table and a merchants table, where each table has 3 columns or attributes and 5 rows or 5 records each. And these two tables have a single column in common, which is called a join attribute. So in this case, the join attribute is the transaction ID. Now, what kinds of queries might we want to issue on joins of tables? Here's an example. So suppose we say that select the pair of records from table 1 and table 2, which are joined on the join attribute transaction ID, where the date is January 2022 and the merchant name is Apple, right? So this is an example of a query that cannot be answered by only searching within a single table, and we would actually need to compute explicitly the join of 2 tables in order to be able to answer this query. And so here in this case, the matching pair of records would be T5 and M1. Note that in each table, we have other records which match the individual queries. For example, T4 also has the date January 2022. And as you can see here, that M4 also has merchant name equals Apple, but these pairs won't be considered as a matching record because the transaction IDs don't match. Now we'll provide a brief overview of our proposal, which is join crosstags. The main feature of join crosstags is that it can handle queries over equijoins of tables without pre-processing any kind of joins at setup. That is, when you are generating the encrypted database as a client, you don't have to prepare the joins of the tables explicitly. It is sufficient that each table, when being encrypted, has a designated join attribute, and any 2 tables which have a common designated join attribute can be joined dynamically, and the query can be sort of executed over the encrypted versions of these tables. The storage overhead for JXT is t-fold if a particular table has t designated join attributes. And as I will sort of argue a bit later, that typically this t is expected to be small in practice for real-world tables in real-world relational databases. Another very attractive feature of JXT is that it can be implemented using purely symmetric key primitives, which means in practice you can implement this entire scheme just using a symmetric key cipher such as AES in an appropriate mode. And JXT also happens to be fully compatible with the large body of SSE that supports other kinds of queries, such as Boolean queries within tables. This means that JXT can be combined with these kinds of schemes to support rich classes of SQL queries over real-world relational databases. Here's a comparison of JXT with the prior art on SSE schemes for joins. And really, it has kind of, there are two previous schemes which were also capable of supporting joins over encrypted relational databases, SPX due to Kamara and Moataz from Asiacrypt 2018, and the more recent proposal from Cash et al. From SENS 2021. And it so happens that JXT is the only one among these which supports join queries without pre-processing of joins at setup. Right? And one of the consequences of this, which I will expand upon subsequently, is that JXT allows extremely flexible table updates on the fly. So now I'll provide a brief overview of the features of JXT. And as I already mentioned, one of the most attractive features of JXT is that when processing the transactions table and the merchants table at setup, you do not need to actually explicitly pre-process the Equijoin of these two tables. You can process them individually. In fact, these tables can be set up and created independently. They don't even need to exist at the same point of time. It is only needed that when creating these tables, we designate that transaction ID is a join attribute over which the transactions table can be joined with any other table that also has transaction ID as an attribute. Then the same for the merchants table. Now, what does this mean? It means that in practice, typically what we have is a small number of candidate attributes in a table with respect to which it is typically joined. For example, a join attribute is typically a primary or a secondary key, which in relational database parlance means that you have a unique value for each record, right? This is an attribute which does not repeat its values across records, or it's a very, very high entropy attribute in the sense that it has almost unique values for all records. And typically such attributes are small in number. Now, what are the advantages of avoiding pre-processing of joins? One of the biggest advantages is that you avoid potential storage blowups due to explicit join computation. For example, suppose that you have table T1, which is tall and skinny, which means that it has many records and few attributes. And you have table T2, which is short and wide, which means there are few records, but many, many attributes. Then their Equijoin over a common attribute is potentially tall and wide. And so the storage required for explicitly storing this Equijoin of these two tables is significantly larger than the sum of the storage required for each of the individual tables. Now in JXT, you would basically have just a small storage overhead per table, but you would not have the storage overhead of explicitly storing this Equijoin table. The other advantage is that suppose that at some point of time, you need to reset up a table, or you need to update a particular table, or maybe you lost a table and you need to recover it. All of this can be done independently. Now, in the prior schemes where you need to explicitly compute joins, you would actually have to recompute the join of a table with every other table in the database with which it can be joined. Whereas in JXT, you don't need to do this recomputation and you can reset up tables independently. And finally, when you join pairs of tables, in the worst case, you could have a quadratic storage blow up in the number of tables, which also JXT avoids. And finally, here's a very brief one-slide summary of the storage and search overheads of JXT. So as I already mentioned, that suppose that a table has a total of n attributes, and let's say T of these are designated as join attributes. And I already argued earlier that T would typically be small in practice. Then the storage overhead of JXT is that you have an ordered T blow up. And in terms of the search overheads, as you can see, the communication cost and the computation cost at the client are actually linear in the individual number of records from each table. Whereas we outsource the expensive and kind of unavoidable multiplicative overhead of the search to the server. And this is really sort of the spirit of outsourced computation, where you have the server do the more expensive computation, right? So, and finally, I would like to mention that, as I mentioned, JXT is compatible with a rich body of work on searchable symmetric encryption that supports a rich class of Boolean queries within tables. Now, together, for example, one such scheme is oblivious crosstags or OXT from way back in Crypto 2013. And now you can combine JXT with these schemes to support more general conjunctive queries over joins of tables, right? So, for example, you could now have, I suppose that the transactions table and the merchants table had more attributes, then you can now have a richer class of queries that you can support using JXT. Now I'll give a very brief technical overview. This will be very informal, and I mainly do it with respect to this toy example. For the details and the proofs, I would refer to the paper. So suppose again that we have the transactions table and the merchants table, and let's say that the only crypto primitive that I will use is a pseudorandom function, which I hope that you are familiar with. And let's consider that F is a PRF family, and let's say that K1, K2, K3, and K4 are uniformly randomly sampled keys. And I'll use these little f, little g, little h0, and little h1 to denote special instances of this PRF with respect to these different keys, right? So for all practical purposes, we can treat them as, independently functioning random functions. So what we do is, as I already said in JXT, we basically process each table in isolation. So let's say we take the transactions table and we take the first record T1. We basically create three variables for this record: an X variable, a Y variable, and a Z variable. The X variable basically stores the ID, which is, let's say, T1. So it basically stores what the identity is, along with just the name of the join attribute, right? Doesn't store the explicit value. And similarly, Y1, it stores the actual, the value which occurs in the join attribute field. And then we have Z, which is basically the XOR of these two values. Okay, so we have these three values. I'll talk about what we do with these, but let's just remember that for each record, we have three values, X, Y, and Z. So we do this for the transactions table, and we do this for the merchants table, right? So remember that these two tables can be set up independently. So we treat them in exactly the same way. And we do this for each of the records in each of the tables, okay? So now let's consider what happens when you actually have a pair of matching entries, right? So this is kind of, we are looking back at it from the point of view of the query, but let's see what exactly happens. So as you can see that each of these entries will have their own X, Y, and Z values. But the interesting thing is that if they match in the join attribute, then the Y values are actually identical. On the other hand, if there are a pair of entries that don't match in the join attribute field, then their Y values are distinct. Okay, and in fact, they are sort of randomly, since these are pseudo-random functions, they are computationally indistinguishable from just two independently sampled random values. Okay, so this is also something that we'll keep in mind. And now here's a very brief overview of what we do. So essentially what we put on the server is a data structure that will, for this purpose of this talk, we'll just consider it abstractly as a key value store. So this is a data structure that stores pairs of keys and values. And given a valid key, the associated value can be sort of retrieved very efficiently. Okay. So there are many realizations of this in practice, but I won't go into the details of how you can implement this. So what we'll do is for each record in the first table, as well as for the second table, we'll basically store a key value pair, which is basically the the corresponding X and Y values, but we won't store them in the clear. Okay. What we'll do is we'll store a sort of one-time padded version of this. I won't go into the details of, like why we do that, but it will be clear as I showcase how we do the search. But we'll just store some one-time padded version of these entries in this key value store, and we'll do a similar thing for the other table as well, right? So we will basically store one-time padded versions of these values. Now, yeah, and this is like a brief overview of how you can actually do it. So what you do is you store these masked X values and Y values in the encrypted key value store. And suppose that I issue a query of the form date equals January 2022, then I can basically efficiently retrieve the masked X and Y values corresponding to T4 and T5, okay, for table T1 separately. Similarly, for the merchants table, if I wanted to issue a query of the form, okay, give me all records corresponding to merchant name equals Apple, then I can again retrieve the one-time padded X and Y values corresponding to the records in the merchants table. And there are many sort of well-known techniques to do this in the SSE literature, like T-sets and encrypted multitypes. Okay. So now the trick is that we actually have also, remember, we have the Z values as well. And now these Z values, we basically store them in a data structure such as a Bloom filter, which allows us for efficient membership testing. So we are not really interested in retrieving the Z values. We are just interested in testing the membership. So now here is an example of what what might happen, right? So suppose we issued this query that find all queries in the Equijoin where we have date equals January 2022 and merchant name is Apple. Now suppose that you retrieve the record T5 from the transactions table. So you have this one-time padded value of X and one-time padded value corresponding to Y. And then you also retrieve the first record from the merchants table because it has merchant name equals Apple, and you have this masked X prime and Y prime values. Okay. And now let's focus on one particular thing, which is that if you remember, since they have the same value in the transaction ID field, they will have the same Y value. So we can replace Y5 with Y prime 1. And now the important thing to note here is I will just focus on these three values which are highlighted: the masked X1 prime value, the masked Y1 prime value, which comes from the transactions table, and this particular Z prime value, which is the XOR of X and Y. Okay. So if we are somehow able to check if X1 prime XOR Y1 prime occurs in the Bloom filter, we are done. But we still have these masks to get rid of. And so at a very high level, what the client would do is it would basically send to the server the XOR of these two masks, right? And this it can do because it knows that it is searching for the date and what date it is searching for and what merchant name it is searching for. What it doesn't know implicitly is what the corresponding join value is. But now we will rely on the fact that if you XOR all these three things, then you basically recover the Z1 prime and you check its membership in the Bloom filter and you would actually get true, okay? Which would indicate that these are a pair of matching records which have the same join attribute value. On the other hand, consider a pair of records which match the individual queries, which is January 2022 and Apple, but they don't match in the transaction ID. Now, in this case, you actually have two distinct Y and Y prime values, which means that when you XOR them, you get a random value, which with very, very high probability does not occur in the Bloom filter, and the membership test returns false. Okay. So this was, of course, a very simplified overview. And in particular, if you send this pairwise XOR of masks, then the client has to do some amount of quadratic work, which we want to avoid. So in the paper, we have additional techniques where we further delegate these pairwise XOR computations to the server, while the client only does linear amount of. Unfortunately, I won't have time to go into the details of this, so I will refer to the paper. And finally, I'll just have a one-slide description of the leakage of this particular scheme. So one leakage that we have is the join attribute distribution pattern. So for example, it leaks the frequency distribution of the values which are taken by the transaction ID across records which are matching the date equals January 2020. Okay. So remember that transaction ID is the join attribute. And so in some sense, you get a histogram of the distribution of the various values of the join attribute across the different matching records in each table. Now, of course, this would not be a leakage if each of these values were unique. Okay. And this is typically the case if the join attribute is a primary key. In this case, all you see is that, okay, it has a unique value in each field, and that's fine because you know that this is a join attribute and you expect it to be a primary key. So if the join attribute is a primary key or it's high entropy, then this leakage is not significant. But if the join attribute is low entropy, if in some case you actually need to join two tables on an attribute which is not a primary key, in this case, there might be issues. There's one way to avoid it, which is you structure the query such that the join attribute is high entropy in the first table, because it is only from the first table that the leakage happens. Maybe the join attribute is high entropy in the first table and low entropy in the second table. In that case, you have a strategy. But if it is low entropy in both tables, then this is a leakage, and we leave it open to further cryptanalysis. And finally, I would like to conclude with some open questions. So we leave it open to extend JXT to flexibly support join over arbitrary attributes. For now, we need a designated set of join attributes at setup. So it would be good to also remove that restriction. It is also sort of an interesting future direction to support queries over equijoins of 3 or more tables, because the techniques I currently showed are for pairs of tables. And finally, we leave it open to extend and analyze JXT further for dynamic addition, deletion of records, and also to implement an experiment over very large databases. Thank you for your attention, and I'll be happy to answer any questions.
Thank you, Sika, for presentation. So any question? We have a short time for one question. Is there any online question? So there's no question, so let's thank the speaker again.
Thank you.
Thank you. Okay, so the last talk in this session is about witness encryption and WinIO from Evasion's LWE by Vinod Vaikutenara, Otegui, and Daniel Wish, and Otegui gives the talk, please.
All right, thank you. All right, so so I'm talking about witness encryption and now I/O. So in program obfuscation or I/O, your goal is to convert a program C into a functionally equivalent program, obfuscated program, with the requirements that if you're given two programs that are functionally equivalent, then the obfuscated program should be computationally indistinguishable. So in this work, we're going to focus on a relaxation or weakening of I/O, which is called now I/O, which has the same correctness requirements, but a weaker security guarantee, namely that the indistinguishability should hold only for now programs, namely these are programs that are rejecting on all possible inputs. Okay, so one reason to study now I/O is that they imply witness encryption, which is a powerful form of public key encryption, where you can use any MP statement as a public key, and you can use any witness for the statement as a secret key to decrypt the ciphertext. So the main results of our paper is simple now I/O and witness encryption schemes that are secure under lattice assumptions. In particular, simple here means that our schemes are reasonably efficient, and they avoid complex non-black box recursion that are used in the state of the art I/O schemes from simple assumptions. Right. Specifically, we analyzed the now I/O and witness encryption candidates from an earlier work with Ile and Vinod, the CVW schemes, and we show that the schemes are secure under the evasive LW assumption introduced in my earlier Eurocrypt paper. Let me just say that there's an independent and concurrent work of Sabari, with some 80% overlap in the results, though my biased opinion is that our constructions are a bit simpler and more modular. And for this talk, I'm going to focus on our now I/O schemes, and starting by telling you about the evasive LW assumption that we use, the description of the obfuscation algorithms, and which takes the input branching programs, and then I'll provide a sketch of the proof of security. So in the evasive LW assumption, we're given two distributions over matrices S and P, and we consider an adversary that gets as input SB plus E for a random matrix, uniformly random matrix B, and Gaussian preimages of P with respect to this matrix B. All right. Note that given these quantities, the adversary can compute SP plus E prime. And the assumption basically says that if the terms are given the first row of the assumption are pseudo-random, then the quantities given in the bottom row are also pseudo-random. As a quick sanity check, we note that the evasive LWE assumption is true from the LWE assumption if S and P are uniform distributions over matrices. So in general, we'll be considering, we'll be using the assumption on distributions that are in fact not uniform. For the applications, we actually require strengthening of this assumption, where the distinguishers get as additional input some auxiliary input that can depend on the matrices S and P, but are independent of the random matrix P. Okay. So to describe our I/O schemes, we first need to talk about branching programs, which are the inputs for our obfuscation programs. for our obfuscation schemes. And here we're going to work with a very simple definition of branching programs, which are specified by row vector U and L pairs of square matrices. And when you evaluate this branching program on a LB input X, we basically take a subset product of the matrix of the M matrices, multiply it by U, and check whether you get the all zeros vector. And if you get the all zeros vector, you accept, and otherwise you reject. And our prior works already showed that if you can obfuscate this very simple class of read-once branching programs, then with a very small overhead, you can also get now IO for general branching programs, as well as witness encryption schemes for MP. Okay, so let me now tell you about the CVW obfuscation scheme for such branching programs. Okay, so the scheme takes a simple branching program and outputs a bunch of matrices C0 and L pairs of matrices Bi sub Bs, where C0 corresponds informally to an encoding of U0, and the D matrix corresponds to a so-called encoding of the M matrix. In fact, the CVW candidate is based on this H15 multilinear encodings. All right, when we evaluate the obfuscated program, we're basically going to take a subset product of these D matrices and multiply by C0 and then do some additional checks. Okay. Let me now tell you how you compute these encodings. The first thing you do is you're going to pick random square matrices. We call them S, and tensor it by these M matrices. Okay. Now, if you try to take a subset product, by the mixed tensor product property, you get basically U times F sub X tensored with this subset product of the S matrices. The next thing you do is you're going to multiply the rightmost encodings by white LWE matrix A sub L. And then the next thing you do, and then that's sort of your evaluation, you are also going to get this extra A sub L term. And finally, you're going to randomize these products by introducing random matrices A0, A1 up to A sub L minus 1, and then cancel them out with their inverses. So here, these matrices are going to be white LWE matrix. And by inverse, I don't mean matrix inverse, but rather I'm going to do this Gaussian pre-images. And then finally, you're going to introduce additional noise terms into all of the D encodings. And I'm going to introduce this, I'm going to denote these noise terms by this squiggly underline. Right? So when you take a subset product, you're going to get the expression over there plus noise. And here, for correctness, require that the matrices M and S as low norm, but that's fine. And it's pretty easy to check that when you do this subset product of the encodings, you're going to get a small value if the program accepts X. And if the program rejects X, you're going to get a uniformly random matrix. So that gives you correctness and functionality. And now let's look at the proof of security. Okay. We want to prove security of this scheme as a now IO scheme, which means that we want to show that if you obfuscate a null program, which is a branching program that is rejecting all possible inputs, so the subset product is non-zero for all possible inputs, then these encodings are in fact going to be pseudo-random under the evasive LW assumption. What do I mean by pseudo-random here? So the C0 encoding is going to look like a uniformly random matrix, and the D matrices are going to look like uniformly random Gaussians. All right, so here's how the proof works. As a first step, consider a mental experiment where you take all possible subset products of the encodings corresponding to all possible evaluations of the program on all possible inputs. Okay? And you take these subset products and you add fresh noise to all of these subset products. Now, what do these two to the L evaluations look like? They're going to look like some sort of like the expression in the on the slide. And what's nice about this expression is that it decomposes into the product of two matrices, where the first matrix is going to be non-zero. In fact, it's going to be full rank matrix because we have a null program. And the second matrix actually corresponds to the BLMR-PRF, which means that it's pseudo-random. And when you multiply pseudo-random matrices with a full rank matrix, you're going to get something pseudo-random. So this allows us to deduce that these 2 to the L evaluations are going to be pseudo-random. Okay, so in the next step, we're going to consider all possible 2 to the L minus 1 evaluations corresponding to all possible L minus 1 bit inputs, the joint distribution of these 2 to the L minus 1 evaluations, together with the 2 rightmost encodings. All right. Now observe that the 2 to the L minus 1 evaluations are going to be of the form something times A sub L minus 1 plus noise, whereas the 2 rightmost encodings are going to be Gaussian pre-images with respect to a sub L minus 1. So this means that we can invoke our RW assumption with the matrix B being a sub L minus 1. And so now when we apply evasive RWE, the if condition corresponds to exactly what we just showed in step 1. And therefore, we may deduce that the Denny condition is true, which basically tells us that this 2 to the L minus 1 encodings are going to be pseudo-random, even given this the rightmost D encodings. So you can repeat this argument, iterate this argument L minus 1 more times with L minus 1 more iterations of the invocations of the evasive RWE assumption. And you get to a point where you can argue that C0 is pseudo-random given all of the D encodings. Okay. At this point, now C0 is completely random, and which means that C0 completely hides A0. And then you can basically run an argument from our earlier paper, which allows you to deduce that all of these D matrices are going to be pseudo-random as well. The basic idea is that since C0 hides A0 now, you can essentially treat A0 as RWE secret to deduce that the first pair of the D encodings are pseudo-random. And that will hide the A1 matrix. And then you can use A1 as RWE secret to argue that the next two D matrices are pseudo-random, and so on and so forth. So now everything is random, and therefore you completely hide the program. This completes the proof of NIO security. Let me conclude. So basically, we showed now IO and witness encryption schemes from the evasive RW assumption. In particular, we analyzed the CVW candidates. Our security proof is going to require instantiate these candidates with slightly larger parameters than in the original candidate. Let me just that's one caveat of our analysis. Along the way, we introduced a new proof strategy for proving witness encryption now IO security. This proof strategy is somewhat different, qualitatively different from, say, the previous work of Gentry, Liu Ko, and Waters for proving security of witness encryption from multilinear maps, where this so-called positional paradigm, where in the proof strategy, they actually require exponential number of hybrids. Whereas in our proof, we only require linear number of hybrids. But what happens is that when we invoke the evasive RW assumption, the size of our instance is actually going to grow exponentially in L. In particular, the dimensions of the matrix S is going to be exponential in L. Right, so let me conclude with a number of open questions. The first is to better understanding the evasive RW assumption, either via cryptanalysis or reductions. The second pertains to the fact that for our analysis, we actually require the evasive RWE assumption with private coin auxiliary inputs. And you can actually show that you can construct contrived auxiliary input distributions based on obfuscation, for which the evasive RWE assumption is false. Now you can the way we handle our proof, you can argue that the distributions we get are not contrived. But another way to get around this contrived issue is to only work with public coin auxiliary inputs. And here we can still ask the questions whether from evasive RWE assumption public coin auxiliary inputs, you can still get some kind of non-trivial now IO and witness encryption schemes. And a good starting point, the recent work of Agrawa et al. From crypto this year. And finally, can you use the techniques in our paper to get to go beyond witness encryption and now IO? Thank you.
Thank you, Otik, for the presentation. And we have plenty of time for questions.
What was this parameter L, which is relevant for this exponential growth of the evasive LWE instance? Yeah, this parameter L. What is the exponential growth in?
Right, good. So the assumption refers to this matrices S and P. When we invoke the assumption, the dimension of these matrices are going to be exponential. So basically, initially when we invoke the assumption, the S corresponds to essentially the concatenation of all of the 2 to the L evaluations. So our matrix S will actually have height 2 to the L. So that's this. So the size of our assumption grows exponentially in L. So for the final analysis, you need to have a very careful setting of security parameters to account for the fact that the size of the instance actually grows exponentially. Yeah, yes.
You went by pretty quickly, but where does your construction break down when? Where does your construction break down when the input program is, for example, 1 on, let's say, even just a sparse number of inputs?
The question is, why does the proof break for non-evasive? That's a good question. So there are 2 ways in which it breaks, but let me say the first one. So here we use the fact that to argue that the 2 to the L evaluations are pseudo-random, we use the fact that the program is
So
rejecting.
the left side won't be it won't be full rank if that product there won't UMX won't be full rank if
Yeah. In fact, it's going to be small. So so you cannot hope for the evaluation to be pseudo-random. The product is going to be a small value and not a uniformly random matrix. Okay, so that's one way in which it breaks down. The other way in which it breaks down is that the evasive RW assumption crucially requires that the distribution of the if condition are pseudo-random. In fact, the evasive RW assumption is false if the distribution of the if condition are not pseudo-random. And for general programs, the condition in the if condition is going to be not going to be pseudo-random. Basically, they're going to be small values. And this is where the so-called zeroizing attacks on IO candidates kick in.
Other question? And there's no online question, and so let's take and own the speaker again.